Right, guys, today we got permutations. Permutations is just talking about how many different ways you can order or arrange things. And that's what I put right here. The study of permutations involves order and arrangement. So when you hear the words order or arrangements, especially later in the week, it always means permutation. Order matters. Order matters. You hear that a lot. Order matters. For example, how many three-letter code symbols can be formed with the letters A, B, and C if you can't repeat them? That is, you can only use each letter one time. So we can have a three-letter code. You can only use each letter one time. You think about it this way. You would have three options for your first letter, but because you can't repeat them, you'd only have two options for your second letter and really only one option for your third letter because you can't repeat them. So all you do in permutations is you multiply those and you would get six. There's six different common permutations. For example, A, B, C would be one, A, C, B, B, C, A. I could keep going here. I guess I will. B, A, C, C, A, B, and C, B, A. That's all six right there. Okay, the next thing is called the fundamental counting principle. This is a big sentence and it's going to sound weird, but it is really so easy. It says if one action can be performed in n ways and is combined with a second action or event that can be performed in m ways, the total number of ways that you can combine those actions is m times n. You just multiply. The fundamental counting principle says you just multiply. Think about the last slide. We multiplied 3 times 2 times 1 while we were counting how many different permutations there were. It's also true for any number of actions, not just two like this up here. You could go 3, 4, whatever. And all you do, multiply the outcomes. You just multiply. That's all the fundamental counting principle is. All right. How many three-letter code symbols can be formed with the letters A, B, C, D, E with repetition? So, again, 3 letters. How many choices do we have for the first letter? We have 5. Now, because we can repeat, we also can choose all 5 for the second and all 5 for the third because we can repeat them. All right, we can do A, or B, 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 but we don't have to repeat them. So we have 5 choices for every single slot or letter. So again, fundamental counting principle, multiply all the different outcomes. So if you multiply 5 times 5 times 5, believe it or not, there's 125 different codes of just 3 letters, just choosing from those 5. So think about the whole alphabet. It'd be 26 times 26 times 26, which is crazy. Okay, permutation and ordered arrangement. We're going to use our calculator sum to find permutations of n objects. And here's what it's going to do. If we're going to do all the objects, there's a button in your calculator. If you go to math, I don't know if you have your calculator with you, if you go to math and go over to where it says PRB at the top, you'll see number 2 says NPR. On your calculator, it actually says this. The reason this slide says NPN is because we're doing all the objects. So this is the formula. To be honest, we're not going to use the formula. We're going to use the calculator, so you won't need to memorize that formula. But really, you're just doing this right here. You're doing n with an exclamation point. I don't know if you know what that's called. That's called a factorial. You don't say n. It means n factorial. For example, 3 factorial equals 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. So on our calculator, it's going to say find 4P4. That's the same thing as this. So there's 2 things you can punch in your calculator. You can hit 4 there's an exclamation point where it says math also. You can hit 4 math, PRB, hit the exclamation point, and it will say 24. Or you could also take your calculator and punch this, and you punch the number 4 first, go to math, PRB, find that button, and then hit 4 again. It will also say 24. So same thing on the second one. You would hit 7 on your calculator, this button on your calculator, then 7, and you should come up with, I'm punching it right now as I speak, should come up with 5,040. That's unreal. There's 5,040 ways to arrange 7 different objects. Okay, in how many ways can 9 packages be placed in 9 mailboxes? 1 package in each box. So order matters. You want to get the package in the right mailbox. So 2 options here. Since you're using all of them, you can do 9 factorial, or you can take your calculator. You can do this. Either way, they're in the same screen. It's probably a little quicker if you're doing all of them to do the 9 factorial. But either if you want to get in the habit of doing the other one, that's okay too. And this is unbelievable. 362,880 ways. Now, for you baseball and softball players out there who think coaches don't make many decisions, if you think about putting 9 people in a batting order, because it's a different order. That's how many different batting orders there are just for 9 players. Now imagine if you have more than 9 players. That's 9 only. Just a freebie there. All right, what if you don't use all of the objects? What if you say, okay, I have 10 objects, but I'm just going to arrange 4 of them? This is the formula we're going to use. This is what your calculator is actually doing, by the way. It's doing n factorial, the number of objects altogether factorial. That is doing that minus the number you're using and using that factorial in your denominator. So on this one that says compute 4p2, your calculator is going to be working this out. It's going to be doing 4 and then 4 minus 2 factorial, which is really this. This is what your calculator is really going to work on. I'm just going to punch it in real quick. 4 math NPR 2, and it's going to give me 12. So again, what this is talking about is if you have 4 objects total and you're only going to arrange 2 out of those 4, how many different arrangements can you have with 2 out of the 4? Right, this is a good example of that. This says the flags of any nation consist of 3 vertical stripes. Suppose there are 9 colors available. How many different flags of 3 can be made without repetition of colors? This assumes that the order in which the stripes appear is considered. So the order matters, and I have 9 total colors available. I can only pick 3 of them. I don't know why I put C. 9, I think for color. I can only pick 3 of them, so I'm going to do 9p3, or how many permutations of 3 objects out of 9? So I'm going to take my calculator again, 9, math, I know I should be showing you this, but it doesn't show it very well on the iPad. So 504, and I'll show you, I'll put it up on the screen for you in class tomorrow and show you exactly the calculator steps. Really no big deal. All right, a couple more. A baseball manager is arranging his batting order. Talked about that a second ago. The 4 infielders will hit first, the 3 outfielders next, then the catcher, then the pitcher. So this is going to be fundamental counting principle and permutations all put together. I'll start here, the 4 outfielders. The 4 outfielders, there are 4 outfielders, and they're going to hit first, so this must be Little League or something. But anyway, there are 4p4 ways that they can hit. That's the orders of all the outfielders, times, these are the orders of the outfielders that can hit. So we have 4 infielders, 4 infielders and 3 outfielders hitting. The catcher's next. That's going to be a 1 because the catcher is only 1 person and the pitcher is only 1 person. So really, I can do this problem just doing those first 2 things, the 4p4 times the 3p3. I think we worked out 4p4 a minute ago, and it was 24. 3p4 was 6, so times 1 times 1. So whatever 24 times 6 is, which is 144. Even with those restrictions on his batting order, there's still 144 different ways he can arrange his order, which is kind of crazy. All right, what if you can repeat? Look at this one. How many 5-letter code symbols can be formed with letters A, B, C, D if we allow a letter to occur more than once? We actually did this a minute ago. 5-letter codes, 1, 2, 3, 4, 5. We're only using 4 different letters though, but if you can repeat the letters, you have 4 choices here, 4 choices here, 4 choices here, 4 choices here, 4 choices there. So you can just multiply those together and you get 1,024. Now, I wrote this down here because if you can repeat the letters or use repetition, really instead of using a P or anything, you can just use how many letters you have and then how many you're going to use to that power, like 4 to the 5th power. And this should be no big deal. One more. All right, this is the last new thing and the last thing altogether. Permutations of sets with non-distinguishable, that's a huge word, objects, which means some of the objects are the same. If that's the case, this is the formula. You do the total number factorial on the top, just like always, but on the bottom, you're going to put all the things that repeat factorial with how many times they repeat. So, for example, this is the best way to show you an example. How many different ways can you write the word Tennessee, or how many different ways can you arrange the letters? Well, think about this. If I switch the N's, it looks the same. If I switch the S's, it looks the same. If I switch the last 2 E's, it looks the same. So what we do is we count the total number of letters, 4, 5, 6, 7, 8, 9, 9 letters in Tennessee. That goes on the top, 9 factorial. In your denominator, you put the number of letters that repeat and how many times they repeat. So there are 4 E's, so I'm going to put 4 factorial. There are 2 N's, I put 2 factorial. There are 2 S's, so I put 2 factorial. And that's how you set that up. Now, the T I don't care about because it doesn't repeat. So one more time. The number on the top is the total number of letters. The numbers on the bottom are the ones that repeat and how many times they repeat. Now, when you punch this in, you must use parentheses around your denominator or it will not work. So I'm punching it in as we speak. Let's see, 4, 2, sorry about this. I should have had this worked out before I did the video. Okay, this is the total number of ways after I get it all punched in, 3780. You may want to take a second as you stop the video and make sure you punch it in correctly on your own calculator while you watch to make sure you got the same thing I did. Anyway, permutations, order matters. It's all about order. Don't forget fundamental counting principle. You just multiply, no big deal. We'll explain it better in class tomorrow. We'll go over it again and do the problems. I'll see you then. Can't wait to see you.